Hello, and welcome back to Calero Academy. Today, we're going to be looking at different ways to find the volume of a cone, and in the accompanying video, we'll try to do the same thing for the surface area of a cone. Okay, so today we're going to be looking at 3 different approaches to find the volume of a cone. We're splitting it into 2 parts. The first part will have those 3 approaches, this part, and the second part will be looking at the 2, you could say, even more interesting approaches. The first 3 we'll be dealing with single variable calculus, and in the second part we'll be looking at some really funky, weird functions, integrating them to find the volume of a cone. Okay, so the first 2 approaches are rather like brothers. They're very, very similar. So, let's look at a right triangle. And remember, the cone we're finding is a right cone, the volume of our cone. So, I'll have a right angle over here, and the length of one leg, we'll call it R, and the length of the other leg, we'll call it H. Now, I'm going to convince you in a couple of seconds that the volume of our cone will be equal to the integral, which is really just a sum, from 0 to H of pi r squared times dh. And 1 second, we should make these guys cap r and cap h. I'll explain that in a second. So the reason that this should be so is that let's look at a random slice of this right triangle. It will have its coordinates will be this little triangle will have a, let's call it cap r. It will have a height, this leg will be equal to cap r, and it will have a run of cap h. So, what is this little slice? When we look at it over here, if we square cap r, and then we multiply it by pi, what we're going to get is the area of a circle. And if we look at our cone, a cone is really just an infinite sum of an infinite amount of different little circles, each with different radii. And cap h and cap r are just arbitrary numbers. Cap h is somewhere along 0 to h, and cap r is somewhere along from 0 to r. So let's put this triangle on a set of axes. One axis over here, one axis over here. It'll have one point on the origin. So all this integral is saying is find the sum of an infinite amount of little circles that are formed by spinning around slices of this triangle around this axis over here. And we'll be integrating it with respect to cap h. So let's look at a little special trick that we can play in here. The first 2 approaches, of course, will look at different ways to plug in values into this to get our correct volume. Okay, let's name this angle over here alpha. In our arbitrary right cone, this alpha is going to remain the same for any value of cap r and cap h. Oh, I should put that differently. Let's look at tan alpha. Tan alpha, we can see, is equal to cap is equal to h on r. But it's not only equal to h on r. If we look closely, this is also going to be equal to alpha, and therefore it will also be equal to cap h over cap r. Any arbitrary cap r and its corresponding cap h will be in this equation. So what we can do is we can get cap r by itself. Cap r is equal to h on tan alpha. And now we're just going to substitute that into this equation. And the reason that is helpful is that we're integrating with respect to cap h, and therefore we want a cap h in there. And tan alpha is just going to, it's a constant for any value. It's going to remain the same since alpha is constant. And therefore, we can just put it outside our integral, which saves us a lot of trouble, because very helpful. So our volume is going to be the integral from 0 to h of pi h squared on tan alpha squared. times d cap h. Okay, so what we do next is simply just put pi and 1 over tan squared alpha outside the integral, integrate h squared, cap h squared, and we'll get h cubed on 3 from 0 to h. And that is going to be equal to pi times h cubed on 3. And let's not forget our tan squared alpha. So we multiply by tan squared alpha. Now, let's remember, tan squared alpha, tan alpha is not only equal to some arbitrary cap h over some arbitrary cap r, corresponding cap r, it's also equal to our dear friends h over r. And we can substitute that in, and what we're going to get is when we substitute tan alpha is equal to h and r in there, we are going to get that the volume is equal to 1/3 of pi r squared h, which ends our first approach. Okay. Now, the second approach is very similar. It's looking at it in a slightly different way. So, it is called the washer method, and everyone loves the washer method, also called the disc method. We call it the washer method because there are these little things in the laundromat, I think. These little discs, which are called washers. And since this is just a load of discs, we just call it the washer method. So, let's look at this guy again. The key to the washer method is simply this. Volume is equal to the integral from a to b of pi f of x squared times dx. This is just the arbitrary formula for it. And the reason of this is that it's saying the same thing as this, except our cap r is defined by a line, by a function. So this allows us to not just looking at this. This is like the simple approach, the common sense approach to approach this problem. This is the general way to look at any function that when we want to rotate it around something. In this case, this volume is going to be equal to the integral from a, which in this case is equal to 0, to b, which in this case is equal to h, of pi times. Now, let's give this careful thought. What is f of x? It's a line, but how do we find the equation of this line? So, we know that the equation of a line is y is equal to mx plus b, where b is the y-intercept, which in this case is 0, and where m is the slope. Now, the slope is defined as the rise over the run. So, we can plug in, the rise in this case is r, and the run in this case is h, so that we can plug in the value of the equation as y, the function, is equal to r on h times x. And that's a function. So we can plug it in here, and we have r on h times x all squared times dx. So that's our washer method. Now, let's just do a little bit of integration here. Let's take our pi, and when we square this, we're going to get r squared on h squared times x squared. We can take out that fraction, r squared on h squared, outside of x squared, the integral of x squared from 0 to h, which is just x cubed on 3 from 0 to h, which is equal to, and we're going to see a great similarity here, it's equal to 1/3 times pi r squared h, which marks the end of our second approach. Okay. Now, this method is not at all related. It's like a second cousin of the other approaches. So, the only thing that's really relating them is that they all involve spinning around, and they both get the right volume. So, it's called the cylindrical shells method. And let's look at this. So, let's look at a new right triangle and a new set of axes just to orient ourselves. So, Let's call this time RH, just for fun, and this R, and it's a right triangle, of course. And we're on another set of axes. Oops, bump that a bit. Okay. The cylindrical shells method, which is this approach, says that volume is equal to the integral from a to b of 2 pi x times f of x times dx. Now, let me explain this a bit. What this is saying, the reason that this is true, is that instead of rotating it around this axis this time, we're rotating it around this axis over here. And what's going to occur when we rotate this around? If we look at this slice over here, when we rotate this around, this is going to get us a very, very small little cylinder. And the area, the area of that little cylinder is going to be 2 pi x times this little guy over here, f of x. And so we're just summing from a to b a lot of these little folks. And wait a second, we are not actually looking at, that was quite embarrassing, sorry about that. We're actually looking at this little slice over here. Forget that I ever said that it was this slice. Sorry about that. Even Calero mentors make mistakes. So, we're rotating this little guy around, and we're going to get a little cylinder. He's actually only a shell of a cylinder. If we imagine it, it's just this little guy round this, like this. And so we call it the method of cylindrical shells. In this case, Ra is equal to 0. So let's start rewriting. It's the volume is the integral from A is equal to 0 to B is equal to R of 2 pi times x times r f of x, which in this case is going to be this line. This function will be defined as h on r times x. You can probably guess that quite easily from what we said in the second approach. So it's that times d of x dx. Okay, but wait a second. The volume that we're calculating here is really all the area around this line rotated around. But that's not what we want. That's going to be a really, really weird solid. What we really want is this area over here. When we rotate that guy around, that's going to be our true volume. So this is just the false profit volume. Our real volume is going to be equal to the cylinder of height r, of height h and radius r rotated around, subtracting the volume of this area rotated around. So let's regroup a bit. It's going to be equal to the volume of the cylinder, which we know to be pi r squared h, because look, when we rotate this huge rectangle around this axis, we're just going to get a cylinder. So that's pi r squared h, subtracting this volume, which we do not want, which will leave us this volume, which we do want. So subtracting the integral from 0 to r of 2 pi x times h on r times x times dx. Now, after a little bit of grunt work, we're going to get that this integral over here is equal to, that integral over here is going to be equal to, first let's write this first, pi r squared h minus 2/3 pi r squared h. Now, the first time I did this problem, I was terrified because I actually forgot that when we just did this integral, we were only finding the volume of this triangle rotated around. So I was really scared. I got 2/3 in there, and I did not know what went wrong. It was a tragedy. But then I remembered it's a cylinder, and subtracting this volume from the cylinder, we're going to get our delightful cone, which in this case will have the volume 1/3 of pi r squared h. And so once again, we've shown that the volume of a right cone is 1/3 of pi r squared h, which marks the end of this approach. Thank you. we're going to do a part B of this same video, and we're going to be looking at some very, very interesting approaches to find the volume. Those two will be very closely related. They're really, really close. They're going to involve multiple integrals, which will be very interesting. I think that will be a first for Calero. And so, thank you for watching today.